So 4.1 is all about exponential functions, and how do exponential functions differ from all the previous functions we've discussed in past units? Let's recall some of examples of functions that we've seen in the past. So in the past, we've seen stuff like, f of x equals 1 half x minus 3. That's a linear function. I think that was unit 1. G of x equals 2x squared minus 6x plus 2. That's a quadratic function. That was part of linear unit 3, I believe. And all polynomial functions. Here's an example of a cubic. X cubed minus 6x squared plus 7x plus 1. And in the same unit, we talked about, rational functions, which was just two polynomial functions divided by each other. So I'm just literally just writing down random letters and numbers here. And heck, we even did square root functions, radical functions, say, the square root of x plus 2 minus 1. Notice how in all of these examples, the independent variable, the x, they were base numbers. For instance, x squared, the variable x is a base that has an exponent. X cubed, the variable is a base that has an exponent. Heck, even a radical function, the x is sort of like on the ground level. It's an object that's being something's doing something is happening to it. Now, what we're going to do today are look at functions that have a particular different structure. Today, we'll look at functions like, f of x equals 2 to the x, g of x equals 3 to the x, h of x equals 1 half to the x. Notice the difference between these function examples here and these function examples. The difference is that the variable x in the yellow examples, I guess I shouldn't have deleted them, in the yellow examples, the x are pushed up into the exponents. And when your variable is up inside the exponent, not surprisingly, we call them exponential functions. So let's go ahead and write down the formal definition of an exponential function. So the definition is the exponential function with base b is defined for all real number x by f of x equals some base to the x power, where the base is going to be greater than 0, and we really don't want the base to be 1. Right? So this is the formal fancy schmancy textbook definition of an exponential function. Basically, anytime your variable x is an exponent on any number that's positive but not 1, we call it an exponential function. And the reason why we don't look at when the base is 1 is we know that 1 raised to any power is going to be 1 itself, so it's just a trivial constant function. Well, like with all new functions we explore, we sort of want to know what the shape is, and the best way to look at what a shape is going to be is just to plot it. I actually want to do two functions at once here. So let's make an xy table, because that's how we analyze functions. But for one function, we'll take a look at 2 to the x. And for the other function, we'll look at his exact reciprocal, 1 half to the x power. And you know me, when I have to pick random x values to plug in, I like to go with my standard -3, -2, -1, 0, 1, 2, and 3. Right. So let's make the f function blue and then the g function yellow. So all I'm going to do, hopefully everyone can understand, all I'm going to do is take these x values here and then just plug them in to the variable. So I'll use a calculator, use your brain if you don't know what the powers are, but I'm just going to do this fairly quickly. So if I take a negative 3 and I plug it into this x here, using properties of exponents, that's going to give me 1/8. And then plug in a negative 2 gives me a 1/4. Plug in a negative 1 gives me a 1/2. Plug in a 0 is a 1. Plug in a 1 is a 2, 4, and 8. If we do the same thing for the g function, take this negative 3, plug it into this x here. That's going to give me an 8. Plug in a negative 2, that gives me a 4. 2 when I plug in a negative 1. 1 when I plug in a 0. 1/2, 1/4, and lastly 1/8, right? So, I mean, very clear pattern has already been established, but let's just go ahead and plot it anyway to see what he looks like. So it looks like for the x values, I don't need a lot of x values, but let's just do a standard 3, 4, 5, 6, 7, 8, 9, 10, 10 by 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're just going to plot points. So negative 3 comma 1/8. I don't know what 1/8 is, so I'm just going to approximate. So here's negative 3 comma 1/8. Let's say it's somewhere down there. Negative 2 comma a quarter, a little bit higher. Negative 1 comma 1/2, a little bit higher. 0, 1, 1, 2, 2, 4, 3, 8. So I hope we can see, even though it doesn't seem like a complete picture, we can see that when we're getting negative, it gets smaller and smaller and smaller. When x is bigger, well, not surprisingly, the graph gets bigger. So it has sort of this like upward growing shape to the right and down shape to the left. So here's f of x equals 2 to the x, and let's just plot the points for the g function. Negative 3 comma 8, negative 2 comma 4, negative 1 comma 2, 0 comma 1, 1 comma a half, 2 comma a quarter, 3 comma an eighth. And it seems to have sort of a backwards relationship here. Ooh, if I can draw better. It seems that as x gets bigger and bigger and bigger, the graph gets smaller, and as x gets more negative, the graph gets bigger. Right? So these are just two examples of an exponential functions. I chose the base 2 and 1/2 just because the numbers are a bit small. But I hope we can make some observations here. Observations, because although these are two separate graphs, they do have some similarities. Right? One similarity is that both graphs seem to have a horizontal asymptote. Specifically, at y equals 0. We can sort of see on the graph here that at the x-axis, y equals 0, the graph seems to hover above that line. Another observation, both graphs go through the point 0, 1. No matter how different the graph is, it looks like they all go through that point there. So that seems, I mean, anytime we have a common point, that's sort of nice for us because it makes the graph predictable. And we can see that the blue graph, f of x equals 2 to the x, it gets bigger as we go to the right. And then the yellow graph, g of x equals 1/2 to the x power, it gets smaller to the right. And we can probably guess why that happens. I mean, the only difference between the blue equation and the yellow equation is the base. The blue equation had a base 2, the yellow equation had a base 1/2, which is a relatively small number. It's a very natural question to ask, well, does that always happen? If your base is, quote, small, do you always shrink to the right? And when your base is, quote, big, do you always grow to the right? Well, instead of repeating this exercise for forever, let's just use Desmos. So here in Desmos, I've already prepared just a couple of, or actually more than a couple, several random examples of exponential functions, and let's see what happens. So the first four examples we can see here, the bases are relatively small: 1/2, 1/3, 1/5, 1/10. Let's see what they look like. So we should know what the first graph looks like, y equals 1/2 to the x powered. That's what we graphed on our notes here. What if I change the base to a third, right? So it does produce a different graph, but it has the same behavior. To the right, we can see it sort of goes down, and to the left, it goes up. Now, it's not a perfect fit, but guess what? They still share that common point of 0, 1. What about if I change the base to 1/5 or 1/10? So we can see here that all these functions, they are slightly different depending on how wide or narrow it is, but they all have the same general shape, and they all go through the special point 0, 1. And what if I make the base relatively big? What if I make the base 2, 3, 5, or 10? So it looks like changing the base does change the narrowness or the steepness of the graph, but it basically has two generic shapes, and it all goes through this point 0, 1. So let's summarize these observations in our notes here. So in summary, oops, change the color. In summary, for graphs of exponential functions, the basic exponential function f of x equals some base the x power for any base greater than 0 but not 1 has a domain of all real numbers, right? In the previous graphs, we saw that it goes forever to the left and to the right, but it has a range of 0 to infinity. Right? It hovers above the x-axis. The line y equals 0 is a horizontal asymptote. And the graph will have one of two shapes. We saw that all exponential function can either grow to the right or shrink to the right. And it all depends on what the base is. If your base is greater than 1, it will grow to the right. And if your base is smaller than 1, it will shrink to the right. We call graphs that look like the left, not surprisingly, exponential growth functions. And we call graphs that look like the right-hand side exponential decay functions. And all that determines if you have a growth or decay is your base. So I emphasize that this is true for all basic exponential functions, but what if we don't have basic exponential functions? What if we have lots of timesing, plussing, minuses, so on and so forth? We have to recall function transformations. This is a list that we've probably written down 5, 6, 7 times, but transformations, it is worth repeating. Because if you know the transformations, you just transform the basic shape. So what are the transformations? The transformations are, if you add to a function, you will move the graph up. If you subtract from a function, you will move the graph down. If you add directly to the x, you move it to the left. If you subtract directly from the x, you move it to the right. If you multiply the whole function, you're going to scale it vertically vertical scale by whatever you multiplied by. If you multiply directly to the x, you're going to horizontally scale by the reciprocal of what you multiplied by. But if that number that you multiply by happens to be a negative, if you multiply the whole function by negative, that's going to be reflection across the x-axis. But if you so happen to multiply the x by negative, that's a reflection across the y-axis. So that is something that we just need to know. Well, and if you do know that, then sketching becomes a piece of cake. For example, suppose I ask you to sketch y equals 3 minus 10 to the x minus 1. The first thing you have to realize is that unless a number is multiplying or dividing by something, it's always a loose separate addition. So this problem or this function may look crazy because of this 3 here, so don't get tripped up. This function is equivalent to y equals negative 10 x to the minus 1 power plus a 3 because that 3 is positive. Now I hope it's very easy to see the transformations. I see a minus here, so that's a flip or reflection across the x-axis. I see a minus 1 with the x, and that goes to the right 1. And I see a plus 3, so that's an up 3. So what do I expect you to do when it comes to sketching? Just apply the transformation on that special point, 0, 1, and apply the transformations on the the horizontal asymptote. So let's go ahead and do this. So the first thing I would do, let's make some tick marks here. Is move your special point. Remember, our special point will always start at 0, 1. So then listen to the instructions. At 0, 1, we're going to completely flip him upside down. So this point will go down here because we got to reflect across the x-axis. Now from this point, we're going to listen to our instructions. Right 1, up 3. So from that point, I'm going to go right 1 and up 3. There is our new point. We're going to repeat the process with the horizontal asymptote. Remember, the horizontal asymptote starts here. So then let's go ahead and flip it across the x-axis. Well, he doesn't move. Let's flip it across. Let's flip it to the right 1. He doesn't move. Let's move this guy up 3. So we can actually do that. We're going to go up 1, up 2, and up 3. There is our new horizontal asymptote, and I'm going to indicate it with a dashed line. There's my new horizontal asymptote. Now we have to remember what the shape is. Remember how the shape of an exponential growth function, and I know it's a growth function because it's a base 10, it's bigger than 1, looks something like that. Well, we flipped him upside down, so you just have to remember that the shape will be flipped upside down, and that will be our graph there. So when I'm grading this, what am I looking for? I'm looking for, do you have the right shape and do you have the right, quote, special point? Let's do another one here. Really quickly here. Suppose I ask you to sketch y equals 4 to the negative x minus 2 minus 3. First thing I need to do is read the transformations. So this is a flip over the y-axis because it's multiplying the x by negative. This right here is to the right 2. This right here is down 3. That's going to be the hardest part of this idea here. This topic is basically, can you read the transformations. So once we have the transformations read, we have to, there we go, draw it out. Move the special point and move the horizontal asymptote. 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's move our special point first. Our special point always starts here. So we're going to flip him over the y-axis. Well, since he's already on the y-axis, he's not going to move. Then from this point, we're going to listen to the instructions, right 2, down 3. So we're going to go right 2, down 3. There's our new points. We're going to do the instructions on the horizontal asymptote. So our horizontal asymptote starts here. So let's flip him over the y-axis. Well, he stays put because he's already symmetrical about the y-axis. Then he's going to go right 2. But since he's already horizontal, he doesn't go anywhere. Now I have to go down 3. So let's go down 1. Let's go down 2. Let's go down 3 here. So that is our new horizontal asymptotes. This right here is the new horizontal asymptote. So then we just have to know what the shape is. Well, the basic shape looks something like this, but he got flipped over the y-axis, so he's got to flip over like that. So he's going to look down to the right and up to the left. That's it. Knowing the shape and structure of these exponential functions should allow you to go backwards. And one thing I'm going to expect you to be able to do is, if I give you a graph, can you come up with the equation? So let's take a look at these next two examples here. Find the exponential function f of x equals a to the x, whose graph is given. So suppose I gave you this growth function here, and I gave you this decay function here. But I do tell you on the growth function, this point is 2, 25. And on this decay function, this point here is 3, 1/8. Well, the trick or the idea is I tell you what the structure is. So notice I tell you that the structure is going to be a basic exponential function. So then if I give you a point, all I got to do is plug it in and just use logic to figure out the bases. Notice how every single point is an x, y. X, y, and you have to remember that f of x is the same thing as y. So if I plug in 2, 25 into the basic structure, f of x equals, let's look at this a example here. I know that the f of x, or the y, is going to be 25, and the x is going to be a 2. So this is asking what base, when you square it, gives you a 25. And then I hope that's very obvious through basic knowledge that means that the a has to be 5. So congratulations, you came up with the function. The function for this given graph is f of x equals 5 to the x. And you basically use the same logic in graph B. If I know that the structure is going to be f of x equals a to the x power, that I tell you that the y value is 1/8, and I tell you the exponent is 3, well, you can just solve it straight up if you can't use mental math. If I want to get a by itself, just take the cube root of everything. And hopefully we can see that the cube root of 1/8 is a half. So the function or the graph of letter B has to be f of x equals 1/2 to the x power. So that's the shape and structure of an exponential function.